If you work in occupational health and safety, your entire job revolves around keeping people safe. But safety itself is a surprisingly slippery concept. What feels safe to an experienced machinist might feel incredibly dangerous to a new hire. It is a subjective state of mind, completely dependent on the person experiencing it. Because of this subjectivity, the historical approach to workplace safety has been a normative science. We rely on value judgments, behavioral interventions, and compliance audits to try and prevent accidents. We end up managing feelings rather than the actual mechanisms of harm. But an accident is not a feeling. When a heavy load drops or a chemical line bursts, that event is governed by objective physical laws. It is measurable, predictable, and firmly rooted in positive physical science. To bridge the gap between subjective safety and objective physics, we look to the energy damage model, developed heavily by Associate Professor Derek Feiner. The model requires a strict change in perspective. It asks us to stop trying to manage the ambiguous concept of safety and instead focus all our attention on the concrete physical process of damage. By treating risk purely as a physics problem, we strip away the behavioral guesswork. We can engineer predictable, systematic controls over workplace hazards, completely independent of human error. Let's look at the physical components of this model. The first is the hazard itself, which this diagram defines strictly as a source of potentially damaging energy. In an industrial setting, you rarely find this energy sitting out in the open. As this cross-section shows, the core energy is encapsulated by a control mechanism. This shell marshals the energy for useful work and prevents its unwanted release. Across from that hazard is the recipient. This blue sphere represents any asset capable of being damaged, whether that is a piece of expensive equipment or a human worker. And here we see a green protective boundary wrapping around that recipient. Every asset has a specific damage threshold, a minimum intensity of energy required to physically breach that boundary and cause an injury or a loss. The physics dictate a simple reality. As long as the energy remains contained within its control shell and the exposure stays below the recipient's damage threshold, an accident is physically impossible. But when controls fail, the energy needs a physical pathway to bridge the gap to the vulnerable asset. We see that pathway represented here by this horizontal energy burst. Weiner calls this connecting bridge the space transfer mechanism. It is the chaotic period where the energy is actively moving through the environment to reach the recipient. This diagram illustrates the first common variation of that transfer, a mobile energy source moving dynamically toward a stationary recipient. Think of a piece of debris flying toward a worker. Conversely, this setup shows a mobile recipient moving into a stationary energy space. A classic example is an operator placing their hand directly into the trapping space of an active machine press. There is one notable exception to this transfer requirement, shown here as coexisting energy. This happens when the energy and the recipient natively share the exact same space, like gravity acting on a worker who has just lost their footing. No travel distance is needed for the damage to occur. By dissecting this exact space-time coincidence, we map the exact sequence of an accident. And once we have that map, we have the exact blueprint needed to intercept it. Now that we have mapped the theoretical anatomy of an accident, we can actively dismantle it using precise physical interventions. Looking at this model, the first control measure targets the hazard itself. As the arrow points to the internal core, the most effective intervention is to completely eliminate or reduce the raw amount of energy present in the system. If the energy must remain, we move to the second control measure. Here, the focus shifts to the purple protective shell, meaning we strengthen and maintain the physical reliability of the hazard control mechanism itself. The third point of intervention deflects the space transfer pathway. If the energy escapes, we install a physical barrier to block the route, or we redesign the workspace to completely remove the need for the hazard and the recipient to share the same space. Finally, the fourth control measure focuses entirely on the green boundary shielding the recipient. This involves hardening the target, often by providing personal protective equipment to physically raise the threshold of damage. Notice what is missing from these 4 steps. There are no posters, no slogans, and no behavioral observations. These interventions represent absolute, objective physical barriers. When organizations step away from subjective safety paradigms and adopt the energy damage model, They gain the ability to systematically and mathematically dismantle the architecture of an accident long before the damage can ever occur.